Every time you log into a website, it feels like one single action, right? You type, you click, you're in. But what if I told you that simple click kicks off a huge cascade of hidden events across all these invisible layers? Well, in this explainer, we're going to put on our hacker hats and peel back those layers to see where the real action is.
Yeah, pretty much everything we do on a computer, whether it's sending an email or whatever, it all starts with something super familiar, just like this login box. It's designed to feel simple, to feel like just one step.
To most of us, this is it. It's a single, self-contained event. You put in your password, you hit enter, the door opens, and you're in. It feels like one action, one result. Simple. But for a security researcher, this isn't the end of the story. No way. This is where the investigation begins. The real truth of what just happened is buried under all these layers of abstraction, and that's where the most critical discoveries are just waiting to be found. So let's start peeling them back.
Okay, the very first layer we're going to peel back is the network itself. We're moving away from the pixels you see on the screen and diving down into the raw information as it literally flies across the wire from your computer to the server.
So your password doesn't just get, shouted out into the void. It gets carefully wrapped in multiple layers, almost like a digital Russian doll. This whole process is called encapsulation. As you see here, first it's wrapped in TCP to make sure it all arrives in one piece, then it's wrapped in IP to get the right address, and only then does it turn into electrical signals on a cable. Each layer adds a critical instruction for the journey.
And how in the world do we actually see this? Well, researchers use tools to do something called packet sniffing. It's basically like putting a stethoscope on the network cable. And suddenly, this invisible digital conversation becomes totally visible, letting an analyst see the raw, structured data for themselves.
So, our little packet makes its journey across the network and arrives at the server. Great, but what happens then? Well, we have to move up to the next layer, the application code that's got to receive that packet and make sense of it all.
And this right here is such a crucial handoff. On the network, the data is just a stream of ones and zeros, right? It's basically gibberish. It's the application's code that has the really hard job of taking that raw stream and correctly parsing it, turning all those meaningless bytes into actual commands and information.
And let me tell you, this parsing step is an absolute minefield for security problems. The code is making all these tiny assumptions about how long a piece of data is, how a number is represented, how text is encoded. A single wrong assumption, just one tiny mistake in that logic, can open up a massive, massive vulnerability.
But okay, let's just say the application is perfect. It parses all the data without a single mistake. It still can't just do whatever it wants. Nope. It's operating inside a much stricter world, one that's constrained by the deepest layer of them all, the operating system kernel. The kernel is the ultimate rule enforcer.
The moment you successfully log in, the Windows kernel creates something for you called an access token. And honestly, the best way to think of this is as your digital ID card. Every single thing you do from that point on is done carrying this token, which proves exactly who you are and what security groups you belong to.
Now, every protected object on the system, we're talking files, folders, you name it, has what's called a security descriptor attached to it. And this is basically a bouncer's guest list. It defines who owns the thing, but more importantly, it has the decal, which says who's allowed to do what, and the SCL, which says what actions need to be logged.
And this all comes together in what's called the access check. Every single time a program tries to access a resource, the kernel security reference monitor does this lightning-fast check. It takes your ID card, your token, compares it against the bouncer's list for that resource, and makes a simple decision, yes or no. This happens thousands of times a second, and you never even see it. Okay, so we've looked at the network, the application code, and the kernel's rules. So where do the really clever, the really severe vulnerabilities actually hide? Well, the answer is fascinating. They're usually not in any single layer. They're in the gaps between them. This right here, this is the core insight of all modern security research. Vulnerabilities aren't just random typos in code. They are systemic flaws. They pop up when one layer, say the application, just implicitly trusts the data it gets from another layer, like the network, without really checking it against its own rules.
And this slide shows you what those broken assumptions look like in the real world. You get things like trust boundary violations, where the code just blindly trusts data from the network, Or logic flaws, where the application's logic lets an attacker skip a critical step, like authentication, before asking the kernel to access something sensitive. You see? These aren't just simple coding mistakes. They are fundamental flaws in how these layers communicate and trust one another.
And that final question, that's what drives all security research. It's this constant process of challenging those hidden assumptions between the network, the code, and the kernel. It's a powerful reminder that real security isn't just some feature you can add on. It's a property of the entire system, one that emerges only when you get every single one of those interconnected layers just right.